So now for something very different. That is the end of the InfoVis part of the module. So this module is quite unique in that we try to cover like information visualization and scientific visualization in the same course. That's very unusual. Usually they're split. Usually you have a module on information visualization or module in scientific visualization. They're generally not combined. Here we're going to actually combine the three topics into one module. So you're going to notice starting now a big shift in the way things look for scientific visualization, and just a change in the content. In the information visualization part of the module, you were given many examples. So we covered many examples, and we didn't go into things in very much depth. There was a breadth kind of aspect to that. Now we're going to not go into as many examples and go into a little bit more depth. Just due to the nature of the subject, some of the scientific visualization algorithms are more complicated and require a little bit more depth. And to start things off, I will not show a slide, but I will show one of my favorite movies of all time. Anybody remember the difference between InfoVis and SciVis? You're supposed to like look away. How about where's Ryan? Ryan, do you remember the difference between InfoVis and SciVis? Could you guess?
Science visualization is many dimensions, so there are data. There are animations and stuff.
Can anybody help out? Help out Ryan? I'm just gonna leave him to suffer a little bit. Anybody remember the difference between information visualization and scientific? How about... He's here. Well, he signed the register. Or did somebody sign it for him? Because that does happen sometimes. Nobody knows. I'll have to... So somebody signed the register on behalf of Jeff. Oh, you're here. Okay, good. You saw what I was about to do? Which I do sometimes. Any idea what the difference is between? You thought you could hide back there in the corner, but now you suddenly realize how much power I hold in my hands. It's like I feel more powerful when I have it in my hands, so you can't so easily hide. Okay, well, I guess I'll explain it then. Information visualization is concerned with abstract data, so data without any inherent geometry. Right? There are no spatial coordinates associated generally with information visualization data, and that's true about like data that's often stored in a database or a spreadsheet. No, not always that way. right? Assignment 1 is mostly information visualization data, like NHS practices. If you don't have the latitude and longitude information, it's not spatial data. If you put it on a map, it turns into spatial data, but you know, most of the data on those spreadsheets is not spatial data. Scientific visualization is concerned mostly with the study of natural phenomena or phenomena that occurs in nature and therefore has an inherent spatial location. And we're about to see some examples, right?
So it's one of the differences that inside is the context is almost always given, while in info is the context we give to it.
Yes, not the context, the coordinates. So in information visualization, you don't necessarily have X, Y, and Z positions for all of your data tuples. And for your data in SciViz, you do. Like an example is just an X-ray. An X-ray, you've all had X-rays, or you know what X-rays are, and you've seen X-rays. That's a scientific visualization of your bones, typically. And that's a natural phenomena, firstly. Well, 99.999% of the time, I suppose you have artificial bones sometimes. And the position of your bones is very important, right? That's what an X-ray is checking. Are your bones in the right position? X, Y, and Z are X, Y, and Z where we expect them to be. That is what an X-ray is for, to check if your bones are in the right position, right? What nature has determined to be a good position.
So the 2 months of London is the subway one, and info base is the other one on SciViz.
Yes, that's a good observation. So the London, the tube map is an info base graph, and the satellite view is a scientific viz, just a photo. That's a SciViz view of London, exactly. Yeah. And here's another one of my favorite examples to start things off. A scientific visualization example, and it combines a lot of the concepts that we've talked about already, like focus and context and overview and details on demand and so on. So you might recognize that object, right? That's a person's head. There's a you know, a person being rendered, but there's another person interacting with the person being rendered, so to speak. There's another person there in a virtual reality context, and they have a clipboard, a virtual clipboard in their hand, and now they're using it as like as a light source, and the shading on the surface of the cadaver is changing depending on what's that? Yeah, that person's no longer alive. Yeah. So one person's alive, and that one's not alive anymore. Right. And they're manipulating the data in this case, right, in a virtual reality environment. So that's the virtual clipboard. Right? They're changing the subset. They just changed the subset of the volume. So from skin to bone tissue. So it's volumetric data, and the position of every data sample is very important. And every data sample has an X, Y, and Z position. And this virtual clipboard has lots of different interaction options, like changing the subset of the 3D data that we're looking at. Right? They can change any subset they like. There are different lighting options. There are different kinds of opacity options. So they've just changed the opacity. So it was fully opaque, and now it's semi-transparent, so we can see through. And they're changing the opacity again, right? The opacity is something, we've already seen that in the angular histograms example, that the user can change the opacity of what they're seeing. This is a different part of the body, right? The torso. There's the rib cage, and there are other tissues. There are soft tissues there, like the kidneys and the lungs. I believe the blue are the lungs and the red are kidneys. My memory serves correctly. And the user can click the volume, right? So they can surround the volume with a cube, and then move the edges of the cube to clip as a clipping plane, and then that lets us see inside the volume a little bit, in some aspects a little bit more clearly. That's also a focus and context example, right? The focus is inside the cube, and the context was outside the cube. Right? This is the user selecting different subsets of the volume data. That's very tricky, right? To select things in a 3D volume is very tricky, right? Because some objects are hiding behind other objects in 3 dimensions, so you might not actually be able to select a piece that's occluded by something else. All right, so I was correct at least about kidneys. And that's the user using the real clipboard as a cutting plane. That's a focus and context visualization, so the kidneys are the focus, and then the rest serves as context. That's the user like rotating the volume with the virtual pen, and then clipping the volume with the clipboard. And there's a beating heart. So that's a time-dependent volume visualization, right, which is not the same as a static one. I still remember the first time I saw this. I was really impressed. I had never seen anything like this before. I saw this, and I was really, really surprised the first time. So that's the user interacting with the time-dependent volume data. It's a beating heart. Did I say that already? And then looking at it from different angles, using the clipping plane and the clipping cube, and so on. Does that look interesting? That's an example of scientific visualization. So it's a natural phenomena, and the position of every data sample is important. Okay, so let's transition then from information visualization to scientific visualization. You'll see it has a different kind of flavor to it. And we're going to start out with the basics, right? What is volume visualization? So scientific visualization is subdivided again into volume visualization, the study of volume data, and then flow visualization, at least in this module. Right? You could have a module dedicated only to InfoVis. You could have a module dedicated only to graphs, GraphVis. You could have a module only dedicated to VolumeVis. And you could have a module only dedicated to FlowVis. And there are some universities that do these subdivisions. I attended a university that had 2 medical visualization modules. So just medical visualization, part 1 and part 2, so a whole year. Okay, so volume visualization is what we're talking about now. It's the study of volume data. Anybody remember what volume data is? An easy Monday evening question, I hope. Anybody remember what volume data is? 3 components. Which 3? X, Y, and Z spatial components, yes. I noticed that Audrey is not with us again. You would think that if your own supervisor was giving a lecture that you would attend that lecture, right? Now, one of the big questions for volume data is you have data that's typically given in a block or a cube. We cannot literally not see every data sample in that cube at the same time. Right? That's just not possible. So we must devise clever mechanisms to select subsets inside the volume. Right? We weren't seeing all the data in the volume in that previous example at the same time. If you tried to say, show me all the data at the same time, you just see the face or the edge of a box, and you wouldn't see anything inside. So there are these different projection techniques that we're going to look at. Maximum intensity projection, slicing, surface extraction, volume rendering, and so on. Those are all ways of selecting a subset of the 3D volume and then projecting it from 3D to 2D, the 2D screen space. Right? And that's essentially what volume visualization is. If you just say it in like 1 or 2 sentences, it's projection techniques for volume data. That's a 1-sentence summary of what volume visualization is. So we're going to be talking about how to select subsets of 3D volume data and project them to 2D. Right? Can we do that interactively? Yes, you've already seen that. Can we do it automatically? Yes, there are ways to do that that are still mysterious for you right now, I think. Usually, the data is scalar data. So scalar data is just data samples with a magnitude. Right? When you go to the doctor and get an MRI scan, you might get, for example, a set of density values in a volume or something like that. So it's scalar data. Usually it's laid out on a 3D Cartesian style grid. And by the way, we're going to be talking a lot about selecting subsets of the 3D data to show. And which subset of the 3D data we show depends on who's doing the looking. Right? You have, I mean, even when you go to see a doctor, usually doctors focus on different parts of the body. Like there's one doctor that's just for the bones, that just cares about the bones. And then there's another doctor that only cares about the muscle tissue. And then there's another doctor that only cares about the brain, for example, and so on. Rarely does Western medicine look at the whole package combined. So that was the long way of saying what we see and what we project depends strongly on the user or the observer, what the observer wants to see. Where does the volume data come from? Well, medicine is a very common source. Computer tomography, magnetic resonance imaging. Wales, southwest Wales got its first MRI machine not very long ago. Actually. Did anybody read about that or remember that? That was kind of, I guess it was kind of a long time ago now, like 10-ish years ago. But up until 10-ish years ago, Southwest Wales did not have an MRI machine. So if somebody needed an MRI scan, they had to go to Cardiff. Nobody, there's one studying medicine that's not here. She might have known that. So, material testing engineering is another source of volume data. Simulation is another source of volume data, anybody have engineering friends? Friends that study engineering? I hope they consider me as a friend at least. Acquaintances, at least acquaintances. I know the names of people that study engineering. Finite element, the finite element method. Anybody ever heard of the finite element method before? That's a good pub quiz question. And you may think, oh, Bob's like on drugs or something. But no, I'm not on drugs. The finite element method was introduced at Swansea University by a very famous engineer. And it's like what put Swansea University on the map. It's the most famous thing that's ever come out of Swansea University. The finite element method from engineering. So it's a funny thing to mention here. Anyways, that's a computer simulation of fluid flow, studying the motion of fluid that we're going to look at. And computational fluid dynamics is the study of fluid flow. And we're going to look at that after the volume viz part of the module. The volume viz data is often, not always. We used to have a lecture just on grids and types of grids, like how the data is stored in 3D space and so on. We took it away because we just don't go into very much depth on that topic anymore. But volume data is usually stored on Cartesian grids. So that means the spacing between x samples along the x-axis is uniform. The spacing along the y-axis between samples is also uniform. And usually the z-axis too. That's what this dx equals dy means. Dx means the distance between samples along the x-axis. And dy means the distance between samples along the y-axis. Sometimes it's not exactly the same on the z-axis, but the goal, it would be nice to have it that way. It's nice to have it that way. And sometimes a data enhancement step makes sure that the spacing between samples is uniform in all three directions. Data can be considered as a cell, looking at the faces of a cube or the corners of a voxel, and we have a special slide on that coming up very soon. There are other kinds of grid structures. This is called a structured grid or a kind of structured grid. But there are other unstructured grids that are not composed of little squares and cubes. They're composed of other shapes like tetrahedra and so on, hexahedra. And those come from engineering. This is sort of medicine, right? All those scanning machines like MRI scanners and CT scanners output kind of friendly Cartesian data, and then the engineering people generate these nasty, unstructured data sets on very more difficult to process grids. Anyone know what a tetrahedra is? Anyone have a guess about a tetrahedra? Are you awake? Sometimes nobody answers. Like somebody. So it's a little pyramid, like a little pyramid. It really, I should just have. If PowerPoint was a little more friendly, I could have just drawn one. But like the keyboard is still stuck in the Stone Ages. So what are some of the challenges? The challenges are the projection, so the projection from the 3D volume onto the 2D space quickly. And there's a lot of data, right? So a typical data set might have, for example, be 512 megabytes. or 512 million data samples, or something like that. And we don't have that many pixels on the screen. We cannot see everything at the same time. And we also want to see that the data is fast. We want to see it quickly because we need to rotate it. If it's sitting in a 3D space, we need to be able to rotate that 3D space and view it from multiple angles. Right? And it's great if we can do that interactively. Right? Interaction is generally considered to be something at 5 frames a second or greater. Here it says 10 frames a second. Real-time rendering is considered to be 20 frames a second or greater, generally. Okay, are there any questions? It looks like we're kind of out of time. Is everybody sad? Stop it there. Don't worry, we're going to continue on Friday. And you can always watch the lectures from last time if you want to see what's going to happen. So yeah, it should help you if you want to catch up. Okay, do you know where I need to sign?
Yes, please, yeah. Fantastic. Thank you very much.
Happy Monday.
I want to ask, the first assignment, I've created a proposal assignment, just because it just provides the names of the banks. That's like, I found the data set that will give me the postcodes. Obviously, I need like the geolocation data, so a big map. I've got around 500, so the geolocations of most of them.
Yeah.
But
Yep.
see, I think there's like 7,000 GP boxes.
Yeah, yeah.
And I'm not allowed to like cache more than, I think it's 700 stored. Do you think that indicates like a proof of concept, or should I just scrap that idea?
No, you can use that as a proof of concept, but it is possible to get all 7,000 NHS practices. They all have a postcode,
Yeah.
and it's then possible to look up the postcode. Somebody has already stored every postcode in the UK
Yeah. I've got
in a spreadsheet.
I've got the postcode spreadsheet. Whereas, so I was using Google originally, they don't like the licensing, they don't like to store cache at all. I found one that lets you store up to 700.
Yeah.
I don't have to pay a subscription to store. Like I could do it anyway.
You missed the lecture where we talked about this, didn't you?
Yeah, I've been ill for the last while, pretty much just been so I do have another option if you want.
No, it's fine, but we went into this in quite a bit of detail
Sorry.
in one of the lectures. It's okay, it's okay. You can find it on the DataViz YouTube channel. I actually go to the website. It's called Freemap Resource. Freemaptools.com.
I haven't written that. Funnily enough, this is the page I think for that lecture.
Tools.com. And then we click on the good old Union Jack. And then we can see a UK postcode with latitude and longitude for every single postcode in the UK.
Right, that's awesome.
Yeah, so it is possible.
Okay, thank you.
Sure.
Also one question, of course. So With certain parts of the data set, you have results that are taken at one point in time and another point in time and another point in time. So you have this sort of range of time. You also have locations or practice and so on. It's really hard not to try and just justify to yourself to just put time and spatial data in on every single one. Is this something you should be doing or something you shouldn't be doing? Just because it's like, well, if I do a trend, then it's more information in there and it's more relevant. Oh yeah, I can put locations in and
Yes, so that's the challenge. I guess a big challenge is could you figure out a way to convey both? Is it possible?
That's like putting them in is fine. It's just should you be putting in data for no other reason than I can put this in, I can have more information in this single visualization.
I would encourage it, yeah. Most people will leave out the time aspect, just leave it out completely. But it's really nice to be able to see.
Currently, so one thing I can find funny with people going, oh, we need longitude and latitude photos at the top. Well, actually, Excel can do photos, and it will make you can project onto them fairly easily.
I have a feeling that Tableau can do postcodes directly as well, because
I've not tried specifically postcodes at Tableau. I've been messing with other things.
Because Tableau has a search function. You can search a map by postcode. So if it has that function, I have a feeling that you could do postcode directly in Tableau. But I haven't actually done it. Anyways, yes, I agree with you in that there are certainly tools that can do something postcodes directly without.
Because one thing we're looking at that is, for example, looking at I think it's the diabetes appointment sort of amount over the course of years mapped against locations, and sort of seeing that there's a spike in 2012 and then it sort of drops down again. But it's an interesting sort of bell curve in various areas. It's higher in high population cities. It's exactly what you expect, to be honest. But then trying to justify not just doing that again for heart issues or something else. It's like, well, why don't I just do the same graph? It's like it's useful information, but it's repeating itself.
Yeah, it is. Yeah, so you need 5 different visual designs for part 1. Yeah, to get full credit at least.
Something will be worked.
I have a feeling that you're going to do very well in the cyber one. That's my psychic prediction.
What's going on? So you mentioned interesting hierarchies. So the first 3 letters of the postcode technically correspond to an area code that make up.
Yes.
There's some 100 or something that make it
Yes.
the UK. Would it be possible to actually use that as a form of hierarchy?
Definitely.
Because you have to manually
Yeah.
split, but that's not too hard to do.
Yes, definitely. Those are naturally hierarchical postcodes.
It seems a little sort of too small, because you essentially have England. All of these subdivisions, and then all the places on the table. So you've only got 3 depth.
If you look carefully into postcodes, I think there are more layers. I think you have something like super output areas, output areas,
So you
super
have
output
the first 2
areas.
letters correspond normally to a county. It depends. There are certain counties that have very weird letters instead, because there was already one that had that. And then there's the number under it, which is the sub-number. So I guess you could do 4.
And there's a lower super output area.
So, for example, Swansea is SA. So SA is the entire, one of the Northern is now sitting there for Swansea. And then the number after that corresponds to which district of Swansea. But the last 3 letters are always just going to be, like, there's nothing sort of, that's just one unique identifier. So you just only got 3 options, you can make sure.
I don't remember, but if you Google like postcode interpretation, you'll find a good description of the inherent hierarchy in there. It would be very cool to see something that looks at that, that shows the different levels. It would be really interesting.
Right. Sorry for asking more questions.
Happy Monday. You have other questions too?
Yes, I did. Sorry for bothering you today. I'm sorry.
It's fine.
Here, I wrote that the largest part of the UK shows the UK.